So remember, a mole fraction, which is represented by an X, tells what fraction of the total number of molecules or atoms that are in a mixture is responsible for the component of interest. So the mole fraction is, in essence, what percentage that particular gas is of the total gas mixture. So we can use that mole fraction, which is abbreviated as X, to determine the partial pressure of that X. Remember that the total pressure that a gas exerts, a gas mixture, is the sum of all of the partial pressures of the gases that are present. Okay, so in order to determine the partial pressure of an individual gas that makes up the pressure, we just need to know how much is there. And this is another way to determine that. It's another way of looking at Dalton's law, but it involves the mole fraction. So what that means is that the partial pressure of a gas depends on the product of the mole fraction of that gas and the total pressure. P1 equals X1 times the total pressure. So let's take a look at an example. This is 11.4. A gas mixture contains 40.0 grams of carbon monoxide and 10.0 grams of nitrogen dioxide. If the total pressure of this gas mixture is 1.2 atmospheres, what is the partial pressure of each individual gas? So what is the partial pressure of carbon monoxide and what is the partial pressure of nitrogen dioxide? So the first thing we need to do is find out what we're given, what equations we're going to need to use, if there are any conversions or anything that we need to do. So if we look at here, right, we know the mass of carbon monoxide in our problem is 40.0 grams. We know the mass of nitrogen dioxide is 10.0 grams. We know that the total pressure equals 1.2 atmospheres. What the problem is asking is the partial pressure of carbon monoxide. Of this total 1.2 atmospheres, how much of that is produced by the carbon monoxide? And then what is the partial pressure of nitrogen dioxide? So those are the two things we're looking. But in order to do that, remember, we're given the mass. If we're going to use the mole fraction, we have to know how many moles of carbon monoxide and how many moles of nitrogen dioxide we have in these samples. So the first thing we need to do is find the molar mass so that the number of moles for carbon monoxide and carbon dioxide can be found for our samples. So what we want to know is how many moles are in 40 grams of carbon monoxide, how many moles of nitrogen dioxide are in 10 grams. So we go back to that standard molar mass. One carbon is 12.0 AMU, one oxygen is 16.0 AMU, for a total of 28.0 AMU. This is the mass of one molecule of carbon monoxide. That tells us that if we weigh out in the lab 28.0 grams of carbon monoxide, that will contain 1 mole of carbon monoxide. And then we can go use that to convert our sample of 40.0 grams carbon monoxide divided by 28.0 grams carbon monoxide, and that will give us 1.43 moles of carbon monoxide. Again, our grams will cancel, leaving us with moles. We should have 3 significant figures. We will do the same for nitrogen dioxide. We have 1 nitrogen atom at 14.0 AMU, 2 oxygen at 16.0 AMU, for a grand total of 46.0 AMU. This is the mass for 1 molecule of nitrogen dioxide. If we weigh out this 46.0 grams of nitrogen dioxide, we will have 1 mole of nitrogen dioxide. This is our conversion factor here, so we'll use that to do our factor label method, right? 10.0 grams of nitrogen dioxide times the fraction 1 mole of nitrogen dioxide divided by 46.0 grams nitrogen dioxide. And again, we want three significant figures, so we have 0.217 moles of nitrogen dioxide. Using these, right, now these are the only two gases. If we go back and look at our original problem, those are the only two gases we have in our problem, right? It's carbon monoxide and nitrogen dioxide. So if we add those two, where are we? If we add those moles together, 1.43 moles of the carbon monoxide and 0.217 moles of nitrogen dioxide, that total number is 1.647, but remember what significant figures for adding is different. We need the least precise number, which means we can only go out to the hundredths position. Since the one beyond that is a 7, we round that 4 up to a 5. We have a total number of moles of 1.65. That's how many moles of gas molecules we have. So now we can use that mole fraction and determine the mole fraction for both carbon monoxide and nitrogen dioxide. For carbon monoxide, we have 1.43 moles of carbon monoxide divided by 1.65 moles, our total moles, and we have 0.867 is the mole fraction for carbon monoxide. For nitrogen dioxide, we take the number of moles, which is 0.217 moles of nitrogen dioxide, divided by the total moles, 1.65 moles, and that will equal 0.132. Now we know the mole fraction. This is what percentage, so a little over 80% of the gas pressure is produced by carbon monoxide. A little more than 10% is produced by nitrogen dioxide. But you've got to go back and look at that original question. They want to know what is the partial pressure of each individual gas. So what equation will we use? Now that we know our mole fractions, we can plug that into our new Dalton's law that relates partial pressure to the total pressure. So, and that just simply states that the partial pressure of a gas in a mixture is equal to the mole fraction of that gas times the total pressure of the mixture of the gas. So for carbon monoxide, we would multiply the mole fraction 0.867 times the total pressure, which was 1.2 atmospheres, and remember the mole fraction doesn't have a unit, and that will give us 1.0 atmospheres. It only has two significant figures because 1.2 only has two significant figures, and the partial pressure for nitrogen dioxide, we take the mole fraction for nitrogen dioxide, which is 0.132, multiply that times the total pressure of 1.2 atmospheres, and that will give us 0.16 atmospheres. And then that is your answer. And you can kind of check your answer, right? If we were to add these two numbers together, we would get 1.16 atmospheres, and we can only, when we add, keep significant figures to the least precise, which this would round to 1.2, which is exactly what our original total pressure is. So that completely agrees with Dalton's law of partial pressure. And that is the end of that problem.